the Earth's core just stopped. Here's what happens next. You know how Earth's day is rock solid, 24 hours? It just twitched. Seismic echoes aren't lining up. Satellites are glitching more over one weak spot, and the inner core looks like it's slowing, possibly backtracking. The explanation is simpler than it sounds. When the core's rhythm changes, the planet's systems feel it. Here's what you'll get: the clean evidence, the core has shifted, why the South Atlantic Anomaly keeps ruining space tech. What breaks first if shielding weakens, real timelines, worst-case solar storms, and the playbook to harden civilization. 2 quick checkpoints to weigh choices. No fluff, constant payoffs. Let's start with the glitch. The glitch is real. Seismic clues and a shorter day. Okay, so basically, if the inner core changes speed, it's like nudging the flywheel inside Earth's engine. You don't see the flywheel directly. You spot what it does to the timing of everything else. Here's what most people miss. We're not guessing. The signal shows up in repeated earthquake paths and in tiny changes to day length. What's the evidence? Seismologists track waves called PKIKP that dive through the solid inner core and come back out. When 2 earthquakes happen in nearly the same place, sending waves along nearly the same path, repeating earthquakes, their waveforms should match at the same stations, and for decades they did. But starting around the late 2000s, those seismograms began to drift. Teams comparing South Sandwich Islands quakes recorded in Canada and Alaska found differences of tenths of a second in the PKIKP arrivals compared with the later core crossing phases. That's the weird part. The only realistic way to shift those timings along those paths is if the inner core's orientation relative to the mantle changed, meaning its rotation rate changed. In other words, the simple version is this. In the 1970s to early 2000s, the inner core was super rotating a little, spinning slightly faster than the mantle. Around 2008 to 2010, it slowed, matched the mantle for a bit, and then began lagging, which from the mantle's point of view looks like a backward drift. Recent analyses, pulling 121 repeating earthquakes between 1991 and 2023, tightened that story. Yes, inner core backtracking relative to the surface is underway now. Everything clicked when I realized they also validated this with another line of evidence. Changes in seismic waveforms from doublets, nearly identical quakes, don't repeat exactly anymore if the mirror they bounce off, the inner core, has rotated to a new angle or changed near-surface structure. Some studies even hint the inner core's top layers are morphing, as well as rotating, which helps explain why some wave paths shift more than others. Now, why should you care about a few tenths of a second in a seismogram? Because that timing shift shows there's real mechanical coupling between Earth's layers. Think of the liquid outer core as the viscous fluid, the inner core as the slow gear, and the mantle as the housing. Electromagnetic and gravitational coupling tug on the inner core, and those tugs can feed back into the planet's rotation slightly. Here's the practical payoff. Astronomers and timekeepers have measured millisecond-level changes in the length of day, and some of that is tied to exchanges of angular momentum between the core and the rest of Earth. Oceans and winds dominate the short-term wiggles, but the core leaves a fingerprint on decadal scales. The counterintuitive part is this. Inner core rotation is not Earth's rotation. Your day isn't suddenly 25 hours. We're talking micro changes, thousandths of a second, buried under the noise of weather and tides. But the fact that we can see any correlation at all means the core is not isolated. It's part of a coupled system that also drives our magnetic field, which is the shield keeping high-energy particles off our atmosphere and your electronics. Micro story time. In the 1960s, scientists recorded seismic echoes from underground nuclear tests. Decades later, when they lined those up against modern earthquake paths, they expected perfect matches. Instead, the core-sensitive arrivals were just off. Not by much, but consistently off in a way that you only get if the target has rotated relative to the mantle or its surface texture changed. That was one of the wait what moments that pushed researchers to revisit the inner core rotation idea with better arrays and more repeating quake pairs. Now, let's keep our accuracy straight. There's debate. Some papers argued for no net rotation, others for steady super rotation, and now a pendulum-like cycle roughly every few decades where the inner core speeds up, slows, and can reverse direction relative to the mantle. The latest work adds data through 2023 and supports the slowdown backtrack model, but uncertainties remain about the exact rate, the role of anisotropy, iron crystals aligned in preferred directions, and How much of the observed change is rotation versus evolving structure at the inner core surface? That nuance matters. Correlation isn't causation. Seeing waveform shifts doesn't tell you the magnetic field is about to flip. It tells you the engine's timing is changing. Here's what most people miss. The first visible consequences of a churning, shifting core aren't underground. They're in space. The magnetic field is generated by flows in the liquid outer core. If the torque balance between inner and outer core changes, it can subtly reorganize those flows over years to centuries. That shows up in the magnetic field we measure at the surface and in orbit. And the weakest, most telling spot right now? A lopsided dent over the South Atlantic where satellites get battered by radiation more than anywhere else in low Earth orbit. Before we jump there, one last clarity check. Are these core changes making today longer? A tiny bit, yes, on the order of milliseconds. So little you won't notice, but enough that timekeeping agencies track leap seconds when needed. The key takeaway is not the day is changing, it's the core is moving relative to the mantle, and we can detect it. That detection is our early alarm that the shield-driving dynamo is in a new phase. If it's real, and the weight of evidence says it is, the first place you see it isn't underground. It's in space, where our magnetic shield is already threadbare in one growing, glitchy zone. The South Atlantic Anomaly, our shield's soft belly. Here's what most people miss. When our magnetic field weakens, it doesn't fade evenly like dimming a light. It gets lumpy. The weakest lump today is the South Atlantic Anomaly, the SAA, a sprawling dent in the field over South America and the South Atlantic where satellites get hammered by charged particles. Why care? Because this is where modern tech fails first. Okay, so basically, Earth's magnetic field traps energetic particles in donut-shaped belts. Normally, low Earth orbit sits below the nastiest flux. But over the SAA, the inner Van Allen belt dips closer to Earth. So spacecraft flying through that region pass through thicker radiation. Think of it like a pothole in the magnetosphere. If you drive there, you hit it. What this actually means in practice, satellites that run flawlessly over Europe suddenly enter the SAA and start throwing bit flips, random ones becoming S in memory, triggering safe modes, data gaps, or corrupted images. Hubble literally avoids taking sensitive UV observations while crossing the SAA. The International Space Station flies through it on every orbit. Astronauts are fine inside shielding, but instruments and computers see more glitches. Spaceflight logs are full of these moments. Resets, star trackers failing to lock, sensors tripping false alarms, clustered over this one awkward patch. Here's the weird part. The SAA isn't static. It's drifting westward and evolving. In recent decades, it's also shown a split-lobe behavior, like the dent is developing a second dimple. That tells you the core-generated field is changing shape, not just strength. Field models built from satellite constellations map this in detail. The local intensity is lower than neighboring regions, and the area of weakness has slowly grown and shifted. Remember this detail. It matters in 5 minutes. Mechanism time, short and sweet. The global field can be approximated by a dipole, but that's only the first-order picture. Superposed are higher-order multipoles from the dynamo in the outer core, plus small contributions from magnetized crustal rocks. When the dynamo's flow patterns reorganize, the dipole can weaken and tilt, and the multipoles can make the field patchy. The SAA is that patchiness made visible in orbital data. Nobody explains this right, but a weaker dipole means the belts sink lower and the boundaries wobble more. Add a multipolar twist, and you get regional dents like the SAA. Why this matters now? If the inner core's rhythm is shifting and the outer core flow responds on decadal to century scales, the magnetic map we rely on keeps morphing. Satellites must harden for higher flux. Operators must schedule safe modes, and mission lifetimes can shorten. Insurance actuaries actually price in anomaly risk. Some low-cost satellites die early, not from drag or battery death, but from cumulative radiation damage made worse in the SAA corridor. Let's make it concrete. Hubble routinely pauses instruments in the SAA to avoid fried detectors. The ISS reports occasional instrument resets aligned with SAA crossings. Commercial satellites log increased single-event upsets there. Occasionally, subsystems latch into safe mode and miss entire data windows. In extreme periods, say during strong solar storms, this region becomes a problem multiplier. More particles, more hits, more downtime. Here's what most people miss about the stakes. The SAA is a local vulnerability, not a planet-wide magnetic flip. But it's the canary, if that. Dent continues growing or splitting, more orbits and inclinations get exposed, and constellation operators, think Earth observation and comms, have to reroute, add shielding, or accept higher failure rates. That means higher costs, shorter lifetimes, gaps in coverage, and service interruptions that ripple down to weather models, navigation corrections, even crop forecasts. Clarify the limit case. A growing SAA doesn't equal an imminent geomagnetic reversal. Paleomagnetism shows flips and excursions take time and are messy, but excursions do correlate with severe dipole weakening and multipolar fields. Basically, SAA-like behavior writ large. We're not there. Today's global field is weakened by about 10% since the 19th century, and the SAA is one strong symptom of that spatial complexity. It's the part you can point to and say, see, the shield isn't uniform. Everything clicked when I realized the operational choreography this forces. Mission planners build South Atlantic quiet times into schedules. Star trackers may be blinded there, so vehicles switch to gyros. Sensitive detectors are powered down. Radiation counters spike, then drop as spacecraft exit the zone. Over years, those operational costs add up, and if the dent drifts west toward busier orbital corridors, expect more coordination headaches and more conservative designs. The counterintuitive part is that ground life stays mostly normal. The SAA's biggest hits are hundreds of kilometers up. Your phone doesn't fry in Rio because of the anomaly, but the data your phone depends on may be more fragile. GNSS signal integrity checks, satellite imagery, climate records, all have to cross that soft belly of our shield. So if the shield's already threadbare here, what breaks first when the core flips phase further or the sun throws a tantrum? Tech breaks are loud. Satellites glitch, GPS gets noisy, aviation reroutes intensify. We'll test that in the next chapter. For now, remember this. The SAA is the live dashboard light telling us the dynamo's output isn't a smooth beam. It flickers and warps. And when the flicker lines up with a solar surge, that's when the pothole becomes a sinkhole. 5 impossibilities, part Y. What breaks first? Here's what most people miss. When the shield weakens, space doesn't politely tap on the door. It pours in. And the first things to fail aren't the ones with the thickest cables. They're the systems that quietly knit everything else together. Let's walk through 3-inch possibilities that are unthinkable until they happen, all physically grounded and seen in smaller forms before. Impossible. 1. The satellite death spiral. Okay, so basically, a weaker, lumpier field lets more charged particles dive lower, swelling the radiation belts and shrinking the safe zone for low Earth orbit. Add a big solar storm, and the upper atmosphere puffs up. Drag spikes. Satellites lose altitude faster, burn more fuel, and some can't correct in time. Meanwhile, electronics take more hits. Single event upsets flip bits. Cumulative dose degrades solar cells and detectors. Here's the weird part. The hits cluster over places like the SAA, so a constellation can look healthy over Asia and then start stuttering over the South Atlantic. In a Carrington-class storm layered on a weakened field, you'd see a bad mix. Dozens of spacecraft in safe mode, some losing attitude control, a few tumbling. Now the counterintuitive cascade, more drag means more uncontrolled reentries, which briefly lowers debris risk. But during the storm, you also get attitude errors and collisions that can seed debris growth. Operators plan for storms, but not for storms riding on a lower, noisier magnetosphere. What this means for you: a single imaging satellite going offline can delay the weather model your city uses tomorrow morning. Large constellations losing a few % of vehicles to drag and radiation translates into slower satellite internet and patchy coverage on the day you're trying to upload storm damage for insurance. For operators, each lost small sat can mean $250,000 to $2 million in hardware, plus launch costs. A medium Earth observation spacecraft can represent $100 to $300 million in sunk costs if it's crippled mid-mission. Impossible. 2. GPS goes squishy right when you need it. What this actually means is the ionosphere, the charged shell that GPS signals pass through, becomes chaotic. A weaker magnetosphere gives solar particles a freer hand, so during disturbances you get scintillation. The signal from satellite to receiver flickers, arrives late or splits. Timing offsets ripple out because GPS isn't just maps. It's the heartbeat for financial trades, cell towers, and power grid clocks. Everything clicked when I realized a few tens of nanoseconds of timing error can nudge a substation's protection relay out of sync or desynchronize high-frequency trading servers. Aviation depends on augmentation systems to clean GPS up. During ionospheric storms, those corrections can lag, or slag. So the map on your phone might look fine, but a survey-grade receiver could slip meters, and a combine's auto-steer drifts rows. Multiply that by thousands of machines, cranes, ships, and you get the quiet chaos of a world mistimed by fractions. Personal stakes. A road construction crew staking property lines can be off by a meter, forcing rework that costs $5,000 to $20,000 in labor and delays. A farmer's RTK guidance, drifting 10 to 20 centimeters during a narrow spray window, can over or under apply chemicals across hundreds of acres, cutting yield by 1-3%. That's $10,000 to $50,000 gone for a mid-size operation in one season. A medevac helicopter on a rural night approach leans harder on inertial and ground beacons when GNSS integrity flags, adding minutes to a critical timeline. Impossible. 3. Polar aviation routes shudder fast. Airlines love polar shortcuts because they save time and fuel. But those paths cut through higher radiation and radio blackouts when the sun acts up. With a softer shield, the dose rate at altitude ticks higher during storms, and HF radio, the long-range backup over oceans, goes dark more often. The playbook already exists. Reroute to mid-latitudes, descend to reduce dose, add fuel stops. The cost isn't just money, it's capacity. A handful of long hauls divert and hub schedules ripple. Crews hit duty limits. Perishable cargo misses connections. During Halloween 2003, we saw this at a smaller scale. With a weaker field, those rare event detours become more common seasonally. The counterintuitive part is this hits medical flights and polar research logistics hardest, small slices of aviation that don't have slack. Tangible hit. A single polar diversion can add $50,000 to $200,000 in fuel and crew costs and burn a precious aircraft rotation. When 10 flights do that in a day, hubs snarl and passengers miss surgeries, conferences, and cargo deadlines they can't easily reschedule. Quick reality check. Impossible here. Doesn't mean fantasy. It means it breaks assumptions we treat as laws, like GPS is always there or satellites fail one at a time. Overlay a Carrington-class CME on today's field and you get compounded. Drag plus radiation, timing noise, plus comms fades, re-reach plus crew timeouts. None of these is extinction level, but together they feel like a slow-motion systems crash. Let's ground this with a rapid case overlay. Take Quebec 89's geomagnetically induced currents. Now scale the driving electric fields up because the magnetosphere has less stiffness. Transformers that would have run hot now saturate. Some trip, a few take damage. Meanwhile, in orbit, operators park birds in safe mode. GNSS integrity flags light up. Precision services degrade for hours. Airlines suspend polar flights and stack up over Anchorage and Frankfurt. Ports pause automated docking that depends on centimeter-level positioning. Pilots go manual and throughput drops. Weather models lose some satellite inputs for a cycle or two. Forecast skill dips right when emergency managers need it. None of these requires new physics, just bad timing and a thinner shield. Costs with receipts. Extra high voltage transformers run $2 to $8 million each and can take 6 to 18 months to replace. A metro-scale day of port slowdowns can burn $10 to $50 million in delays. A single national GNSS correction outage can cost construction and agriculture sectors tens of millions in lost productivity in a week. Here's what most people miss about finance and grids in that swirl. Both depend on tight time. Phaser measurement units and grids sample voltage and current with GPS timestamps. If timing drifts, operators lose the glass cockpit that shows grid health in real time. Markets rely on time order. If clocks jitter, they slow or halt. It's not that money vanishes, it's that transactions back up and confidence wobbles. The fix is redundancy, terrestrial timing and hardened references, but many systems haven't finished that upgrade. Pause for thought. You get to save one technology class for the next decade, fully harden it against weak field storms. Which do you pick and why? GNSS timing, high voltage transformers, or low Earth orbit comms? Drop your choice and your rationale. There's no perfect answer. Each buys a different kind of stability. Clarify the frame before we shift to biology later. These are loud, visible breaks. They grab headlines, the biological impacts, ozone thinning, radiation dose, move slower, and hide in baselines. We'll separate signal from story when we get there. For now, the takeaway is simple. When the core's rhythm slips and the sun throws a punch, failures synchronize. The job isn't to predict the exact punch, it's to break the synchronization. Deep time signals, flips, excursions, and extinctions. Here's what most people miss.